Imagine a cosmic siren song, a whisper across the void promising salvation, a perfect echo of home. For generations, humanity has gazed upon the stars, dreaming of a Goldilocks Zone, a celestial cradle where life, just like ours, might thrive. But what if that zone, that perfect embrace, is not a haven, but a meticulously disguised tomb? 2,000 light-years away, nestled within the temperate glow of a sun-like star, lies Kepler-22b. A world envisioned as a vast, shimmering ocean, its surface an unbroken sapphire mirror reflecting a perpetual alien dawn. From a distance, it is the epitome of cosmic hope, a liquid jewel floating in the infinite. The data tells us it exists, a planet perhaps twice the size of Earth, bathed in the warmth essential for liquid water. Yet, within those inviting depths, evolutionary pathways might have diverged into a nightmare, forging horrors we are utterly unprepared to comprehend. The very conditions for life could, in fact, be the blueprints for its most terrifying forms. If the deepest mysteries of the universe and the dark secrets they might conceal stir your curiosity, remember to like this video, share your thoughts in the comments, and subscribe to Terran for more journeys into the cosmic unknown. Prepare yourselves, we begin. For centuries, the cosmic ballet of stars and planets remained a distant, unknowable spectacle. Our understanding of life's prerequisites was confined to the singular, astonishing example of Earth. Yet, with the advent of powerful telescopes and sophisticated detection methods, humanity's gaze pierced the veil, revealing an astronomical truth that redefined our place in the cosmos. Exoplanets are not rare anomalies, but an ubiquitous feature of every star system. This revelation ignited the profound quest for Earth-like worlds, a search often guided by the concept of the habitable zone. The habitable zone, often romantically dubbed the Goldilocks Zone, represents the orbital sweet spot around a star where conditions are neither too hot nor too cold for liquid water to persist on a planet's surface. It is a fundamental concept in astrobiology, acting as the primary filter in our preliminary search for extraterrestrial life. This liquid state of water is not merely a preference, but a biochemical imperative. It serves as the universal solvent, facilitating the complex chemical reactions that underpin all known biological processes. Without it, the intricate dance of organic molecules necessary for life's emergence and sustenance simply cannot occur. The boundaries of this zone are, however, far from static. They are dynamically shaped by the luminosity and temperature of the parent star. A hotter, more massive star, like a blue giant, radiates immense energy, pushing its habitable zone further out into its system, demanding planets orbit at greater distances to avoid vaporization. Conversely, cooler, dimmer stars, such as the ubiquitous red dwarfs, possess habitable zones that hug their stellar surface, requiring planets to orbit incredibly close to maintain warmth. Our own Sun, a stable G-type yellow dwarf, provides a convenient reference, anchoring its habitable zone at an optimal distance that allows Earth to flourish. The Kepler Space Telescope, launched in 2009, revolutionized this search. Its mission was to stare fixedly at a single patch of sky, observing the subtle dimming of thousands of stars. This transit method allowed astronomers to detect exoplanets as they passed in front of their parent stars, momentarily blocking a fraction of their light. Each tiny dip in brightness offered a glimpse into another world, providing data on planetary size and orbital period, and critically, whether that orbit fell within the star's life-giving habitable zone. The sheer volume of data collected by Kepler transformed our understanding of planetary demographics, demonstrating that potentially habitable worlds are not exceptions, but possibly the rule. It was against this backdrop of accelerating discovery that Kepler-22b first entered the scientific lexicon in December 2011. Its announcement sent a ripple of excitement through the scientific community and captivated the public imagination, for here was an exoplanet that seemed to check almost every box on the checklist for potential habitability. Orbiting Kepler-22, a G-type star remarkably similar to our Sun, in spectral classification, this distant world appeared to be an almost ideal candidate for harbouring liquid water and, by extension, life itself. Kepler-22b's parent star, Kepler-22, is slightly smaller and cooler than our Sun, but crucially it belongs to the same class of stable G-type stars. This stellar similarity implies a consistent energy output over billions of years, a crucial factor for the gradual evolution of complex life. Unlike the tempestuous red dwarfs, which can bombard their close-orbiting planets with deadly flares and intense radiation, Kepler-22 offers a serene, long-lived beacon, providing a steady stream of light and warmth. This long-term stability is not merely a bonus. It is the fundamental bedrock upon which any sustained biosphere must be built. The planet's orbital period, approximately 290 Earth days, placed it squarely within its star's habitable zone. This meant that, theoretically, its surface temperatures would be conducive to the existence of liquid water. Initial estimates suggested an average surface temperature of around 22 degrees Celsius, 72 degrees Fahrenheit, assuming an Earth-like atmosphere and greenhouse effect. Such a temperature range is not only ideal for water, but also comfortably within the bounds for most terrestrial biological activity, mirroring the conditions found in many of Earth's thriving ecosystems. Furthermore, Kepler-22b was estimated to have a radius approximately 2.4 times that of Earth, positioning it firmly within the super-Earth category. These planets are larger than our homeworld but considerably smaller than gas giants like Neptune, suggesting they could possess solid surfaces and potentially retain substantial atmospheres. The combination of a stable star, an optimal orbital distance, and a potentially rocky or liquid surface ignited fervent speculation that Kepler-22b could be humanity's first concrete glimpse of a true Earth 2.0, a twin world brimming with alien life. This confluence of favourable characteristics led many to hypothesize that Kepler-22b might be a vast ocean planet, a water world where a global sea stretched across its entire surface. Without large landmasses to disrupt currents or create continental weather patterns, such a world could maintain a surprisingly stable and temperate climate, further enhancing its perceived habitability. The sheer abundance of liquid water, the very elixir of life, seemed to promise an environment ripe for biological flourishing, perhaps even an ancient, deep-seated biosphere unlike anything we could find on Earth. The scientific community's initial enthusiasm for Kepler-22b was palpable. It represented a tangible triumph in the search for extraterrestrial life, moving the concept from abstract theory to observable reality. It became a symbol of humanity's enduring hope to find companionship in the vast emptiness of space, a shining beacon promising a shared destiny. Yet, this very optimism, fueled by limited data and boundless imagination, inadvertently obscured a deeper, more unsettling truth. The allure of the habitable zone and planets like Kepler-22b lies in their resemblance to Earth. But in the alien vastness, resemblance can be a cruel illusion. End of hook section. The year 2011 marked a pivotal moment in humanity's ongoing narrative of cosmic discovery. After years of meticulously observing faint, distant starlight, the Kepler Space Telescope delivered a name that would echo through scientific journals and popular consciousness alike. Kepler-22b, announced by NASA, this exoplanet instantly soared to prominence, heralded as one of the most compelling candidates for a truly Earth-like world discovered at that time. Its unveiling was not merely another entry in an ever-growing catalogue of alien worlds. It was a beacon, a tantalizing whisper from the void that suggested we might not be alone in the grand tapestry of life. The initial excitement surrounding Kepler-22b was rooted in a constellation of seemingly ideal characteristics, beginning with its parent star, Kepler-22, located approximately 620 light-years from Earth in the constellation Cygnus, is a G5-type star. For context, our own Sun is a G2 type, making Kepler-22 a slightly smaller, slightly cooler, yet fundamentally similar stellar neighbour. This spectral similarity was, and remains, profoundly significant. G-type stars are renowned for their long, stable lifespans, offering billions of years of consistent energy output, a crucial prerequisite for the slow, arduous process of biological evolution to unfold from simple origins to complex ecosystems. Unlike the volatile red dwarfs, prone to unpredictable and devastating flares that could strip away planetary atmospheres or sterilize nascent life, Kepler-22 promised a serene, enduring warmth, a gentle cosmic hearth where life might comfortably simmer for eons, This stellar stability set the stage for Kepler-22b's most celebrated attribute, its orbital position. With an orbital period estimated at approximately 290 Earth days, Kepler-22b resides squarely within its star's habitable zone. This precisely calibrated distance meant that, assuming a sufficient atmosphere, surface temperatures could hover within the critical range for liquid water to exist. Early models, relying on broad assumptions about its atmospheric composition, projected an average surface temperature of about 22 degrees Celsius, or 72 degrees Fahrenheit. Such a temperature profile resonated deeply with our terrestrial experience, evoking images of balmy oceans and temperate climes, making the prospect of a vibrant, watery world incredibly compelling. It was a projection of comfort and familiarity onto a distant, enigmatic sphere. Furthermore, the planet's estimated radius of roughly 2.4 times that of Earth placed it firmly within the category of super-Earths. This designation describes planets larger than our homeworld but smaller than the gas giants of our own solar system. Super-Earths are theoretically diverse, ranging from rocky behemoths to dense ocean worlds, and their increased mass grants them a greater gravitational pull, enhancing their ability to retain a substantial atmosphere. A robust atmosphere is more than just a breathable envelope. It acts as a planetary blanket, moderating extreme temperature swings, distributing heat across the globe, and providing a vital shield against harmful stellar radiation and cosmic impacts. The implication for Kepler-22b was clear. Its size suggested a world capable of fostering and protecting the very conditions essential for sustained life. The confluence of these factors, a stable, sun-like star, an orbit within the habitable zone, and a size conducive to retaining an atmosphere, quickly cemented Kepler-22b's image in the public consciousness as an almost perfect Earth 2.0. The prevailing hypothesis, fueled by these tantalizing data points, was that Kepler-22b was a colossal water world, a global ocean extending across its entire surface, potentially hundreds of miles deep. Such an environment, teeming with liquid water under a relatively benign star, seemed to be an ideal crucible for life. The very idea sparked a cascade of speculative visions: vast sunlit seas teeming with alien fish, photosynthetic organisms blooming in aquatic forests, and perhaps even complex multicellular creatures evolving beneath its endless waves. Yet this dazzling initial portrait, painted with the brushstrokes of hope and limited observational data, may have been a profound deception. The term habitable zone itself, while scientifically precise in its definition of liquid water potential, carries an inherent anthropocentric bias. It reflects our understanding of life, a singular example in a universe of infinite possibilities. What we often overlook is that habitable does not automatically equate to benign, nor does it guarantee safety or even a recognizable form of life. The data that thrilled us was merely a whisper, an echo from afar, offering tantalizing clues but concealing a multitude of complex, potentially lethal realities. The precise mass of Kepler-22b, for instance, remained elusive for years after its discovery, while its radius suggested a super-Earth. Its density, and therefore its composition, was subject to wide-ranging theoretical models. These models hinted at a far more substantial mass than initially assumed, possibly dozens of times that of Earth. This crucial detail, though often overshadowed by the excitement of its habitable zone location, holds immense implications for everything from its internal geology to the very nature of its surface and the life it might support. A higher mass means dramatically increased gravity, an environmental stressor of profound consequence. Moreover, the initial temperature estimates were based on a simplified atmospheric model, often assuming compositions similar to Earth. In reality, the atmospheric dynamics of a super-Earth, especially one potentially dominated by water, could be vastly different. A thicker, denser atmosphere, rich in certain greenhouse gases, could trap heat far more efficiently, pushing surface temperatures far beyond the comfortable 22 degrees Celsius, even within the habitable zone. Conversely, a planet's albedo, how much light it reflects, could also significantly alter its thermal balance. The shimmering, inviting ocean might actually be an endless cauldron, or a perpetually stormy expanse, shaped by forces far more extreme than anything found on our temperate homeworld. Kepler-22b therefore stands as a monument to both our ambition and our naivete. It is a world whose initial promise, a dazzling deception of familiarity, masks a deeper, more profound alienness. The very parameters that rendered it so appealing for life may, in fact, be the ingredients for a biosphere evolved to an existence so extreme, so inimical to human biology, that its discovery could transition from a symbol of hope to a chilling testament to the universe's indifferent and sometimes terrifying diversity. The gold in the Goldilocks Zone, we're beginning to realise, might actually be fool's gold. End of hook section. The dazzling prospect of Kepler-22b as a true Earth 2.0 hinged critically on a singular alluring hypothesis that it is a majestic ocean planet, a world entirely enshrouded by a global sea. This vision, born from the absence of discernible land masses in our limited observations, paints a picture of an unbroken sapphire sphere, its surface a vast shimmering expanse under an alien sun. Such a world, devoid of continents and land-based topography, stands in stark contrast to our own geologically dynamic Earth, where the relentless grind of tectonic plates carves out mountains, trenches, and the very foundations of diverse biomes. The implications of a truly global ocean are profound and far-reaching, fundamentally reshaping every aspect of the planet's environment. Without continents to break up ocean currents or to act as thermal regulators, a water world like Kepler-22b might experience a remarkably stable, albeit perhaps uniformly warm, climate across its entire surface. The vast thermal inertia of such a colossal body of water would act as an immense heat sink, absorbing and distributing solar energy with unparalleled efficiency, potentially mitigating extreme temperature fluctuations that plague planets with fragmented landmasses. This steady thermal environment, seemingly ideal for life, also eliminates the diverse ecological niches created by continental shores, vast deserts, or towering mountain ranges, funneling all evolutionary pathways into the aquatic domain. However, the depth of this conjectured ocean is where the true alienness of Kepler-22b begins to reveal itself. Planetary models suggest that on a super-Earth like Kepler-22b, with its larger mass and greater gravitational pull, the sheer volume of water could be immense. We're not merely talking about Earth's average ocean depth of 3.7 kilometers. Instead, we could be envisioning a global sea tens, perhaps even hundreds of kilometers deep. At such crushing depths, the very properties of water begin to transform in ways alien to our terrestrial experience. Under the immense hydrostatic pressure exerted by miles of overlying water, liquid water begins to behave in extraordinary ways. Deep within Kepler-22b's ocean, far below the photic zone where sunlight can penetrate, conditions would be utterly inimical to anything resembling Earth's surface life. The pressure would be so profound, reaching megabar levels, that ordinary liquid water would be compressed into exotic high-pressure ice phases. These are not the familiar buoyant ice cubes of Earth, but crystalline structures like Ice 7 or Ice X, which are stable at temperatures far exceeding the boiling point of water, yet remain solid due to the overwhelming pressure. Imagine a planet where the ocean floor is not solid rock, but a gargantuan layer of hot, high-pressure ice, underlying a layer of supercritical water, where distinct liquid and gas phases cease to exist. This stratification would create a planetary interior utterly unlike Earth's, with unique mechanisms for heat transfer from the core, potentially driving massive underwater volcanic activity or hydrothermal vents that dwarf anything found in our abyssal plains. This deep ocean chemistry would be governed by extreme conditions, fostering unique mineral interactions and releasing exotic chemical compounds into the water column. The absence of land also means a drastically different hydrological cycle. On Earth, land masses facilitate the formation of rain shadows, diverse weather fronts, and the recycling of atmospheric moisture through terrestrial ecosystems. On an ocean world, the entire atmosphere would be in constant, intimate contact with the water, leading to perpetual high humidity and a dense, hazy atmosphere perpetually saturated with water vapor. This would create a global climate characterized by continuous, heavy rainfall and violent planet-spanning storms, driven by the ceaseless evaporation and condensation cycles of an endless ocean. The sky, seen from the surface, might be a perpetual brooding grey, filtered by thick clouds that obscure the distant star, casting the entire world in an eternal twilight. Furthermore, the very chemistry of such a global ocean could be radically different from Earth's. Without continents to weather and erode, supplying a steady stream of minerals and nutrients, the deep-sea geochemistry would be dominated by hydrothermal vents, volcanic outgassing, and interactions with the planet's core. This could lead to an ocean rich in heavy metals, sulfuric compounds, or other elements that would be toxic to terrestrial life, yet potentially essential for an alien biosphere. The ocean, initially perceived as a life-giving cradle, could instead be a vast corrosive chemical soup, its waters biting and alien. The sheer volume and depth of water also impact the penetration of light. Even if Kepler-22b's atmosphere allows for adequate light transmission at the surface, the vast majority of its ocean would exist in absolute darkness. The photic zone, where photosynthesis can occur, would be confined to a comparatively thin uppermost layer. Below this, life would need to rely on chemosynthesis, deriving energy from chemical reactions, or on the slow, steady rain of organic detritus from above. This creates a vast, lightless abyss, a biological frontier where evolutionary pressures would favour organisms adapted to extreme pressure, perpetual darkness, and potentially scarce resources. This deep ocean hypothesis transforms Kepler-22b from a gentle, Earth-like paradise into a world of crushing pressures, perpetual twilight, and potentially alien chemistry. It is a world where the very definition of habitable is stretched to its breaking point, demanding a re-evaluation of what constitutes an environment capable of sustaining life. For any terrestrial organism, these conditions would represent an insurmountable barrier, a lethal environment of unimaginable hostility. But for a biosphere that has evolved over billions of years in such an environment, these extremes would be home, forging life forms of profound resilience and chilling adaptation, forms that might render our wildest nightmares pale in comparison. The seemingly tranquil surface could hide an unimaginable, terrifying underworld. End of hook section. The tranquil image of Kepler-22b as a shimmering ocean jewel belies a far more profound and potentially terrifying reality: the inescapable tyranny of its immense gravitational pull. While its radius, estimated at approximately 2.4 times that of Earth, initially positioned it as a super-Earth, a larger, more robust version of our homeworld, the implications of its mass extend far beyond mere size. Planetary science dictates that a world of this dimension, especially one potentially rich in water and heavier elements, would possess a mass significantly greater than Earth's, leading to a crushing surface gravity that would redefine the very act of existence. Consider the raw physics. If Kepler-22b holds a density comparable to Earth's, its volume would imply a mass upwards of 13 to 14 times that of our planet. This staggering mass translates directly into a surface gravity that could be more than twice, perhaps even 3 or 4 times, stronger than what we experience daily. Imagine every movement, every breath, every heartbeat contending against an invisible, unrelenting force constantly seeking to pin you to the ground. This isn't merely a minor inconvenience, it is a fundamental environmental parameter that would sculpt every aspect of the planet, from its geological underpinnings to the very form and function of any life that might arise. On a geological scale, such immense gravity would fundamentally alter the planet's internal dynamics. Earth's dynamic tapestry of towering mountain ranges, deep oceanic trenches, and constantly shifting continents is a direct consequence of plate tectonics, driven by the slow convection currents within its mantle. On Kepler-22b, the increased gravitational compression would likely suppress or dramatically modify these processes. A thicker, more rigid lithosphere, the planet's outer rocky shell, would resist the forces that drive plate movement. Subduction, the process where one tectonic plate slides beneath another, might be far less efficient, leading to a planet with less internal heat recycling and potentially a less vigorous magnetic field. The result would be a surface largely devoid of dramatic topographic variation. No majestic Everest-like peaks, no Grand Canyon-esque chasms. Instead, models suggest a comparatively flat, uniform landscape, subtly undulating beneath the pervasive ocean. Its geology muted by the overwhelming weight of itself. Volcanic activity, while potentially still present, might manifest as widespread, effusive flows rather than explosive mountain-building eruptions, due to the difficulty of magma breaking through such a compressed crust. This gravitational dominance extends deeply into the planet's atmospheric and oceanic systems. While a high-gravity world boasts the advantage of retaining a dense atmosphere, preventing it from bleeding into space, this retention comes at a cost. The air itself would be far heavier, exerting immense pressure at the surface. For any hypothetical terrestrial life, this would be like constantly existing at the bottom of a deep terrestrial ocean, with the very air pressing down with suffocating force. This dense atmospheric blanket would also scatter light more intensely, potentially casting the surface in a perpetual muted twilight, even under a direct sun. For Kepler-22b, hypothesized as a vast ocean world, gravity's role is even more profound. It dictates the sheer depth and pressure of its global sea. On Earth, our deepest trench, the Mariana, plunges to nearly 11 kilometers, where pressures are over 1,000 times that at the surface. On Kepler-22b, with its greater mass and radius, the oceans could easily descend for tens, even hundreds of kilometers. At these unfathomable depths, the pressures would exceed anything found on Earth by orders of magnitude, reaching levels where even the most resilient deep-sea creatures would be crushed into molecular paste. As explored previously, these pressures would transform liquid water into exotic high-pressure ice phases, forming a solid, hot seabed beneath an impossibly deep, highly pressurized liquid layer. This planetary architecture creates an environment where the concept of ocean floor is redefined as a dynamic interface between supercritical fluids and incredibly dense crystalline water. Now consider the implications for life itself. Any organisms evolving under such crushing gravity would be fundamentally alien to our understanding. Terrestrial life, as we know it, would be a biological impossibility. A human standing on Kepler-22b, if they could even withstand the atmospheric pressure, would immediately collapse, their bones shattering, their internal organs liquefying under the unbearable weight. The sheer energy expenditure required for any movement would be astronomical. Therefore, life would have to adapt with extreme ingenuity. Structural support would be paramount. Creatures might evolve incredibly dense, heavy skeletons, perhaps composed of exotic minerals, to prevent collapse. Alternatively, they might adopt hydrostatic skeletons, like those of Earth's jellyfish or worms, but scaled up to an unimaginable degree, relying on incompressible fluids to maintain their form. Bodies would likely be compact, flattened, or radially symmetrical, minimizing surface area exposed to the relentless downward pull. Movement would be slow, ponderous, and energy-intensive, or exploit buoyancy and currents with extraordinary efficiency. Large, towering land animals, a hallmark of Earth's evolutionary history, would be impossible. Evolution would favor squat, sprawling forms, or those intimately integrated with the liquid medium. Even small-scale biological processes would be impacted. The circulation of fluids within an organism, the very pumping of blood, would demand incredibly powerful hearts and circulatory systems to overcome the immense gravitational resistance. Waste expulsion, nutrient absorption, and even cellular division would be energy-draining endeavors. The evolutionary pathway would relentlessly select for metabolic efficiency and a profound understanding of how to manage weight and movement in a high-gravity field. Flight, a biological triumph on Earth, would likely be an impossible dream, unless the atmosphere was so extraordinarily dense it provided near-liquid buoyancy, allowing for slow, powerful glides rather than true flight. The pervasive, unrelenting force of gravity on Kepler-22b transforms a potentially habitable world into a domain of profound biological challenge. It is a world where mere survival is an athletic feat, where every organism is a testament to extreme adaptation against an invisible, omnipresent adversary. The weight of existence would be a literal crushing burden, shaping a biosphere of incredible resilience and terrifying forms, utterly foreign to our fragile low-gravity experience. The beautiful shimmering ocean of Kepler-22b could thus harbour a silent systemic horror, a world where gravity itself is the most brutal and unforgiving predator. End of hook section. The notion of Kepler-22b as an idyllic ocean paradise, nurtured by a sun-like star, begins to unravel further when we delve into the intricate dance of its atmosphere, temperature, and the potential for a truly corrosive chemistry. The habitable zone might grant the potential for liquid water, but it provides no guarantees about the nature of that water, the air above it, or the light that filters through it. Instead, the very conditions that seem inviting from afar could converge to create an environment of perpetual twilight and searing, toxic depths. Given Kepler-22b's larger size and formidable gravity, its atmosphere would likely be far denser than Earth's. This increased atmospheric mass would exert immense pressure at the surface, a crushing weight that would be profoundly challenging for any Earth-like life form. Imagine existing permanently at an atmospheric pressure equivalent to Earth's deep ocean trenches, where the air itself feels like a thick, viscous fluid. This density would not only create a suffocating physical environment, but also profoundly alter light penetration. Solar radiation, instead of piercing through with clarity, would be scattered and absorbed by the sheer volume of atmospheric gases and perpetually suspended water vapor. The result would be a world shrouded in perpetual twilight, even at midday. The distant star, Kepler-22, would appear as a diffuse, hazy orb, its light filtered through layers of thick clouds and dense atmospheric haze. This is not the crisp, bright illumination that fuels Earth's surface photosynthesis, but a muted spectral glow that pervades the upper reaches of the ocean. For organisms reliant on light, this would necessitate extreme adaptations, perhaps evolving hyper-efficient photosynthetic pigments capable of capturing every stray photon, or shifting to entirely different metabolic strategies. The absence of direct, intense sunlight would profoundly limit the extent of the photic zone, the narrow band near the surface where light can penetrate sufficiently for photosynthesis. Below this upper layer, the vast majority of the ocean would exist in absolute eternal darkness. Compounding this environmental challenge is the question of temperature. While Kepler-22b lies within the habitable zone, initial estimates of a balmy 20 Cygni 70 studi assume an Earth-like atmospheric composition. However, a super-Earth with an extensive global ocean could easily possess an atmosphere rich in potent greenhouse gases, perhaps carbon dioxide, methane, or even exotic compounds derived from its deep ocean chemistry and geological activity. A denser atmosphere, coupled with an abundance of heat-trapping gases, could easily lead to a runaway greenhouse effect, transforming the planet into a scalding inferno. Even if the surface temperature remains relatively moderate, the deep ocean could retain vast amounts of heat, creating a world where the lower layers are far warmer and more thermally active than the surface. This thermal stratification would be extreme, with superheated zones coexisting with more temperate upper layers, constantly churning and interacting. The true nightmare, however, might reside in the very chemistry of Kepler-22b's oceans. On Earth, our oceans are continually replenished and balanced by the erosion of continental landmasses, bringing in a diverse array of minerals and elements. On a global ocean world, particularly one with suppressed tectonic activity due to immense gravity, this continental input would be virtually absent. Instead, the ocean's chemistry would be predominantly driven by hydrothermal activity, volcanic outgassing from the planetary interior, and the interactions with a deep, high-pressure ice mantle. This could lead to a primordial chemical soup utterly unlike anything in Earth's seas. Imagine oceans saturated with heavy metals, highly acidic due to an excess of sulfur compounds from extensive volcanism, or laden with exotic salts and minerals that leach from the high-pressure ice formations. The sheer scale of such an ocean means that these chemical properties would be pervasive, not localized. A corrosive chemistry would define the very medium of life, forcing any organisms to evolve extreme resistance, perhaps utilizing unique biochemical pathways or protective exoskeletons to withstand environments that would instantly dissolve terrestrial organisms. For example, if the planet experiences significant deep-sea volcanism, it could inject vast quantities of sulfuric acid, hydrogen sulfide, or other highly reactive compounds into the water. These chemicals, while potentially serving as energy sources for chemosynthetic life, would render the entire ocean toxic and hostile to carbon-based life as we know it. The water itself might be more akin to a dilute acid or an alkaline solution, constantly reacting with any exposed organic matter. Proteins, cell membranes, and DNA, the very building blocks of Earth life, would rapidly denature or break down in such an environment. Furthermore, The interaction between the deep, high-pressure ice layers and the overlying liquid water could introduce further chemical complexities. As exotic ices melt and reform under fluctuating pressure, they could release novel compounds or sequester essential elements, radically altering nutrient availability. This creates an environment where chemical stability is constantly challenged, demanding extreme adaptability from any native life. The very water that makes Kepler-22b potentially habitable could be a lethal cocktail, a corrosive bath designed to dismantle all but the most resilient and profoundly alien forms of biology. Thus, the perpetual twilight abyss of Kepler-22b is not merely a descriptive phrase, it is a chilling encapsulation of a world where light is scarce, temperature gradients are severe, and the fundamental chemistry of life itself is redefined by an unforgiving corrosive environment. This is a planetary crucible that would forge life forms of unparalleled toughness and alien design, creatures whose very existence would be a testament to the universe's boundless capacity for both creation and horror. The shimmering jewel from afar, upon closer inspection, reveals itself as a colossal, churning vat of unimaginable peril. End of hook section. If life were to emerge and endure on Kepler-22b, it would be a testament to evolution's boundless capacity for adaptation, but also a chilling demonstration of how radically alien biology can become under extreme pressure. On a world defined by crushing gravity, perpetual twilight, and potentially corrosive chemistry, the anatomy and physiology of its inhabitants would be honed by environmental forces far beyond our terrestrial experience. This is not a world for delicate carbon copy organisms, it is a crucible for biological fortitude, forging creatures whose very existence would defy our conventional understanding of life. The dominant force shaping all life on Kepler-22b would undoubtedly be its immense gravity. Terrestrial animals have evolved skeletons and musculature to counteract a single G of gravitational pull. On Kepler-22b, where gravity could be 2 to 4 times Earth's, the fundamental challenge is structural integrity. Any organism would need unparalleled strength to simply hold itself together. We would expect to see life forms that are predominantly flattened, sprawling, or inherently amorphous, distributing their mass over a wider area to reduce localized stress. Imagine deep-sea organisms on Earth, like anglerfish or viperfish, but scaled up and structurally reinforced to an extreme degree. Skeletons, if they exist, would be incredibly dense and robust, perhaps composed of ultra-hard, mineralized composites unknown on Earth, rather than calcium-based bone. These would not be light, hollow structures, but heavy, compressive frameworks designed to bear immense loads. Alternatively, hydrostatic skeletons relying on internal fluid pressure for support might be prevalent, but these would need to be exceptionally strong to resist both external water pressure and the planet's gravity. Imagine vast, gelatinous forms, akin to colossal jellyfish, but with internal support structures of chitin or superdense cartilage, lending them a terrifying, slow-moving resilience. Musculature would be disproportionately powerful, designed for brute force to overcome inertia and gravity with every deliberate movement. Locomotion would likely involve slow, powerful contractions or the exploitation of currents, rather than rapid, agile bursts. Beyond gravity, the deep ocean environment presents a suite of other profound challenges. The perpetual darkness, extending for tens or hundreds of kilometers below the photic zone, renders vision as we know it largely useless. Instead, life would evolve highly sophisticated chemosensory systems, detecting subtle chemical gradients in the corrosive water to locate prey, mates, or escape predators. Electroreception, detecting the faint electrical fields generated by other organisms, might also be a dominant sense, allowing creatures to see through the murk. Mechanoreceptors, sensitive to pressure waves and vibrations, would be crucial for navigating and hunting in an environment where sound travels efficiently, but sight is impossible. These sensory organs might be distributed across broad, sensitive membranes, or concentrated in specialized appendages, allowing for a comprehensive, multispectral perception of their dark world. The extreme pressure would also dictate cellular and molecular architecture. On Earth, high pressure can denature proteins and disrupt cellular membranes. Life on Kepler-22b would need uniquely adapted macromolecules, proteins folded in ways that maintain stability under megabar pressures and cell membranes composed of lipids that resist compression and maintain fluidity, their cellular machinery would be inherently robust, designed to operate in an environment that would instantly rupture terrestrial cells. This could involve novel forms of osmoregulation, maintaining internal cellular pressure against the overwhelming external force, perhaps by accumulating pressure-stabilizing osmolytes or having incredibly rigid cell walls. The corrosive chemistry of the ocean, saturated with heavy metals or caustic compounds, would necessitate advanced detoxification mechanisms. Organisms might evolve biological shields, secreting protective layers of mucus or calcified armor to prevent direct contact with the toxic water. Internal organs would need specialized enzymes to neutralize harmful chemicals or sequester them in inert compartments. Perhaps their very biochemistry would be founded on elements resistant to such corrosion, incorporating metals or silicates into their metabolic pathways, or utilizing entirely different solvent systems than water for their internal chemistry. This could mean life that, at a fundamental level, is structurally and chemically incompatible with Earth-based biology. Metabolism in the lightless depths would be predominantly chemosynthetic. The primary energy producers would be extremophilic microbes, analogous to Earth's vent bacteria, deriving energy from the chemical gradients produced by deep-sea volcanic vents, or the interaction of water with the hot, high-pressure ice mantle. These microbial mats would form the base of the food web, supporting a complex ecosystem of grazers and predators. These chemosynthetic autotrophs might harness energy from sulfur compounds, heavy metals, or even exotic radioactive elements, creating a truly alien biological engine. Considering the extreme conditions, the concept of a multicellular organism on Kepler-22b leads to chilling possibilities. We might envision enormous, slow-moving filter feeders anchored to hydrothermal vent fields, their vast bodies designed to process immense volumes of corrosive, nutrient-poor water, or, conversely, highly mobile, streamlined predators, their dense bodies perfectly adapted to slice through the high-pressure liquid, propelled by powerful paddle-like limbs. Their digestive systems would be incredibly robust, capable of processing the tough, mineralized tissues of their prey, or breaking down the complex, potentially toxic organic compounds derived from chemosynthesis. Their reproductive strategies would also be adapted to the deep, dark ocean, perhaps involving the release of incredibly resilient spores or the incubation of offspring within specialized, pressure-resistant internal chambers. Evolution in the extreme on Kepler-22b would not merely create diverse life, it would sculpt an entirely new paradigm of biological existence. It would be an anatomy of the abyssal architects, where every feature, from molecular structure to macroscopic form, is a ruthless optimization for survival in an environment that actively seeks to crush, dissolve, and starve. These are not creatures that would merely survive, they would dominate, utterly alien and horrifying in their perfect adaptation to a nightmare world. End of hook section. In the crushing perpetual gloom of Kepler-22b's abyssal oceans, where light is a forgotten myth and pressure reshapes matter, the struggle for survival would inevitably give rise to apex predators of chilling efficiency. These are not the familiar sharks or whales of Earth, but biomechanical marvels, perfectly honed instruments of death forged in a crucible of extreme gravity, darkness, and corrosive chemistry. Their very existence would embody the planet's latent horror, a testament to evolution's indifference to beauty and its singular focus on lethal adaptation. Imagine a vast, multi-layered ecosystem, its base fueled by chemosynthetic organisms clustering around volcanic vents or spread across the high-pressure ice formations. These primary producers, perhaps vast mats of extremophilic microbes, would support a chain of specialized grazers and detritivores, who in turn become prey for creatures higher up the food web. The apex predators would occupy the pinnacle of this dark hierarchy, their forms and senses refined over billions of years of relentless competition in an environment that allows no weakness. Given the planet's immense gravity, these hunters would be built for power and resilience, not speed or agility in the terrestrial sense. Their bodies would be dense, streamlined for efficient movement through a highly pressurized, viscous liquid. Forget skeletal structures designed for verticality. These creatures would likely be broadly flattened, perhaps disc-like or elongated, with massive hydrodynamic fins or powerful undulating body segments providing propulsion. Their musculature would be hyper-developed, capable of generating immense thrust to overcome both water resistance and the ever-present downward pull of gravity. Their internal organs would be encased in incredibly tough, flexible membranes, and their circulatory systems would be capable of pumping vital fluids against staggering internal and external pressures. Their sensory apparatus would be a marvel of bioengineering, far surpassing anything found in Earth's deep-sea fauna. In a world of absolute darkness, eyes would be vestigial or entirely absent. Instead, these apex hunters would navigate and hunt using an array of non-visual senses. Highly refined mechanoreceptors, distributed across their skin or concentrated in sensitive tendrils, would detect the faintest pressure waves, vibrations, or turbulence generated by prey. Imagine a predator that can feel the distant thrum of a swimming organism, or the subtle displacement of water caused by a struggling victim from hundreds of meters away. Electrolocation would be another dominant sense. Similar to Earth's electric eels or certain sharks, these creatures might generate weak electrical fields and detect distortions caused by other life forms. This allows them to create a detailed three-dimensional electrical map of their surroundings, identifying prey even when camouflaged or hidden. Furthermore, highly specialized chemoreceptors, far more sensitive than any terrestrial equivalent, would detect the minute chemical signatures of fear, injury, or metabolic byproducts, essentially allowing them to smell their prey from vast distances through the corrosive ocean. Some might even possess magnetoreception, using the planet's magnetic field, if present, for long-range navigation across featureless expanses. The methods of attack would be equally terrifying. Lacking agility, these predators would rely on brute force, ambush, or specialized weaponry. Some might possess powerful, crushing jaws designed to shatter the dense exoskeletons or internal skeletons of their prey, much like a cosmic nutcracker. Others might employ extensible, barbed proboscises or powerful, venomous stingers capable of delivering paralyzing neurotoxins into the high-pressure circulatory systems of their victims. Bioluminescence, while potentially used for communication or attracting mates, could also be weaponized, blinding flashes to disorient prey, or subtle, shifting patterns to lure unsuspecting victims into lethal proximity. Consider a creature like the Leviathan of the Deep, a massive, slow-moving predator perhaps hundreds of meters long, its body a dark, mottled mass of incredibly tough, leathery hide, studded with pressure-sensitive pores. It moves with ponderous grace, its vast bulk propelled by rhythmic undulations, a living shadow against the faint, persistent glow of chemosynthetic vent fields. Its head is a broad, flattened plate, lined with rows of bioluminescent lures that pulse with hypnotic alien light, drawing in smaller organisms. Hidden within its gaping maw, however, are not teeth, but interlocking plates of an unknown super-hard mineral designed to shear and grind through the densest biomass. Its primary hunting strategy is not pursuit, but patient, silent ambush, waiting for the slightest ripple in the water, the faintest electrical signal, before its colossal maw snaps shut with a force that creates a localized cavitation shockwave, stunning or crushing anything in its path. Or perhaps the abyssal harvester, a more active hunter, resembling a gigantic multi-limbed squid, its body armoured with thick chitinous plates. Each of its powerful limbs is tipped with a cluster of electroreceptive sensors and hollow, hypodermic-like spines, capable of injecting a potent, highly corrosive acid that liquefies organic matter on contact. It would stalk its prey, its movements precise and energy efficient, using its electromagnetic sense to pinpoint victims in the gloom. Once a target is acquired, it would unleash a volley of bioluminescent bursts to disorient, then strike with lightning speed, injecting its corrosive payload, dissolving its prey into a nutrient-rich slurry that it then absorbs. These are not creatures that would inspire awe. They would inspire existential dread. Their existence is a stark reminder that life, even in its most successful forms, can be utterly indifferent or even hostile to our own delicate biology. The apex predators of Kepler-22b's abyssal plains would be the ultimate expression of adaptation to a nightmare world, silent, systemic killing machines, each a living monument to the terrifying beauty of an indifferent cosmos. The Goldilocks Zone may promise life, but it never promised life that would be anything less than horrifyingly, perfectly alien. End of hook section. Beyond the immediate threat of monstrous predators, the true insidious horror of Kepler-22b might lie in the very fabric of its planetary metabolism, a pervasive, systemic threat woven into the biosphere itself. This isn't about individual hunters, but a planetary-scale biochemical warfare, where the environment itself, shaped by unique geological and biological processes, generates conditions fundamentally lethal to anything alien, especially human life. The habitable zone becomes a misnomer, a cosmic trap where the very air, water, and even the microbial life act as silent systemic agents of destruction. On Earth, our biosphere maintains a delicate balance, recycling elements like carbon, nitrogen, and oxygen through a complex interplay of geological and biological processes. But on Kepler-22b, under its unique conditions of immense gravity, deep oceans, and exotic internal chemistry, this planetary metabolism could be radically different, producing environmental hazards that are not merely inconvenient, but fundamentally toxic. Consider the atmosphere. While its dense nature might be advantageous for retaining gases, the composition itself is unknown. If the dominant life forms rely on chemosynthesis driven by, for example, sulfur-rich hydrothermal vents, the atmosphere could accumulate vast quantities of hydrogen sulfide, sulfur dioxide, or other noxious gases. Even if oxygen is present as a byproduct of some alien photosynthesis, it might be in concentrations that are either too high or too low, or combined with other gases to form compounds that are respiratory poisons for terrestrial organisms. A human breathing the air of Kepler-22b could immediately suffer acute chemical poisoning, its lungs dissolving, its nervous system seizing, a death far swifter and more agonizing than mere asphyxiation. The atmosphere, a life-giving envelope on Earth, could be a silent, suffocating toxin cloud on Kepler-22b. The oceans themselves, as hypothesized earlier, could be a corrosive chemical soup. This isn't just about localized areas of acidity, it's about a global solvent system that has evolved to sustain alien biochemistry but dismantles terrestrial biology. If the waters are rich in heavy metal ions, potent acids, or highly reactive alkaline compounds, any direct contact would be devastating. Imagine attempting to immerse human skin or equipment in water that swiftly corrodes metals and dissolves organic tissue, not through slow decay, but rapid, violent chemical reaction. Survival suits would need to be of unprecedented resilience, constantly monitored for breaches, as even microscopic leaks could be catastrophic. The very act of touching the ocean could be an act of self-annihilation. Furthermore, the planet's deep-sea geological activity could perpetually infuse the oceans and atmosphere with highly dangerous substances. If Kepler-22b's core is rich in highly radioactive elements, the extensive hydrothermal systems could bring radioactive isotopes to the surface, dispersing them throughout the global ocean and atmosphere. This would create a radiation-soaked environment, silently corrupting cellular structures and leading to inevitable, agonizing death from radiation sickness. The gentle warmth from its star combined with such internal heat might just be masking a perpetually irradiated death trap. The pervasive biological threats extend beyond the macro scale. Even if the environment were physically survivable, the ubiquitous microbial life of Kepler-22b could pose an invisible systemic horror. Earth's ecosystems are built on a delicate balance of nutrient cycling, decomposition, and symbiotic relationships, often mediated by bacteria and fungi. On Kepler-22b, these same essential processes would be carried out by alien microorganisms with entirely different biochemistries. These biotoxins could be a silent, omnipresent threat. Imagine a pervasive form of alien plankton or chemosynthetic bacteria that, as a metabolic byproduct, releases compounds that are potent neurotoxins to humans, causing rapid paralysis or agonizing seizures. Or perhaps alien fungal spores, ubiquitous in the atmosphere or surface waters, trigger violent allergic reactions or invade terrestrial cells, replicating uncontrollably within an immune system utterly unprepared for such an invasion. These are not targeted attacks, but the incidental systemic byproducts of an alien life system simply existing, metabolizing, and evolving. The very concept of a food chain takes on a terrifying dimension. If any terrestrial organisms were introduced, They would not only struggle against gravity and pressure, but would also contend with a completely alien nutrient base. Even if seemingly edible, the alien biology could be built from chirality-reversed amino acids, or contain compounds that are indigestible, toxic, or even mutagenic to human physiology. Eating could literally be poisoning oneself, a slow, inevitable descent into organ failure and genetic corruption. In essence, Kepler-22b's planetary metabolism could have evolved into a perfectly tuned, self-sustaining system of systemic biowarfare against any foreign biological intrusion. It is a world whose inherent processes, its very breath and blood, could be a silent, all-encompassing threat. The beautiful, shimmering ocean could be a vast biological weapon, its depths and atmosphere saturated with unseen perils. The planet itself, a living entity, actively hostile, not out of malice, but out of its own indifferent existence. The habitable zone is merely a stage, and on Kepler-22b, the play is a tragedy for any who dare to step upon it uninvited. End of hook section. Beyond the physical and chemical dangers, the most insidious, terrifying threat on a world like Kepler-22b could be an invisible one. The silent, relentless peril of alien biological and immunological threats. If life has indeed emerged and thrived in its crushing depths, it would have evolved biochemistries and cellular structures utterly foreign to anything on Earth. This profound difference doesn't just mean incompatibility, it could signify an existential immunological warfare, a microscopic planetary-scale threat that could dismantle human biology with horrifying efficiency. On Earth, our immune systems are marvels of evolutionary engineering, honed over billions of years to recognize and combat pathogens. But this recognition is deeply rooted in terrestrial biochemistry. Our bodies are primed to identify specific molecular patterns, proteins, and genetic sequences that are characteristic of Earth-based viruses, bacteria, and fungi. When confronted with an alien pathogen from Kepler-22b, our sophisticated defenses would likely be utterly blind. They would encounter biochemical structures, genetic material, and replication mechanisms so profoundly different that they would either fail to recognize a threat at all, allowing it to proliferate unchecked, or react with a devastating, self-destructive immunological cascade. Imagine microscopic entities, alien viruses, bacteria, or even more complex cellular parasites, whose proteins are folded into enantiomeric forms, mirror images of the amino acids found in terrestrial life. Our enzymes would be unable to interact with them, our antibodies unable to bind. They could slip through our biological defenses unnoticed, replicating rapidly, hijacking our cellular machinery with impunity. These pathogens might utilize novel nucleic acid analogues, entirely different genetic codes, or even silicon-based instead of carbon-based metabolisms. Such fundamental differences would render every antiviral, antibiotic, and medical intervention we possess utterly useless. The horror would not necessarily stem from malicious intent, but from sheer biological indifference. These alien pathogens would simply be doing what all life does, seeking resources, replicating, and adapting. For them, human cells might represent an unimaginably rich, untapped resource, a perfect defenseless host. A single airborne spore, a microscopic organism ingested with contaminated water, or even a superficial contact with an alien biofilm could unleash a pandemic beyond the grasp of terrestrial medicine. The initial symptoms might be subtle, mimicking common ailments, until the infection becomes systemic, irreversible, and ultimately fatal. The immunological threat isn't limited to pathogens. Even inert alien compounds could be lethally dangerous. The unique biochemistry of Kepler-22b's lifeforms might produce complex organic molecules that are potent allergens or toxins to humans, even without being metabolically active. Inhaling trace amounts of alien pollen-like particles, ingesting water containing certain algal byproducts, or even touching a surface coated with alien microbial secretions could trigger severe anaphylactic shock, agonizing neurological damage, or rapid organ failure. Our bodies, adapted to Earth's specific biological palette, would be overwhelmed by the alien chemistry, reacting violently to substances our biology has no framework to process or defend against. This invisible barrier raises profound ethical and practical dilemmas for any future interstellar exploration. Landing on a potentially inhabited world like Kepler-22b would not be an act of discovery, but a precarious dance on the knife edge of biological catastrophe. Every breath taken, every surface touched, every sample collected could be the vector for an unknown, uncontrollable plague. Quarantine protocols would need to be absolute, bordering on the impossible, given the microscopic nature of the threat. The very air carried back on equipment, the residue on clothing, could be enough to contaminate an entire planetary biosphere. Conversely, the threat is bidirectional. Just as alien life could be lethal to us, terrestrial life could be devastating to a native biosphere on Kepler-22b. Our own microbes, bacteria and viruses, harmless or even beneficial to us, could be catastrophic invaders on an alien world. The history of Earth provides a sobering precedent. The introduction of European diseases to indigenous populations in the Americas, or invasive species into isolated ecosystems, often resulted in widespread death and ecological collapse. Imagine human explorers inadvertently carrying terrestrial bacteria into Kepler-22b's oceans, unleashing an unstoppable cascade of disease and ecological disruption that decimates an ancient alien biosphere. We could become the silent accidental destroyers, bringing not exploration, but extinction. The silent but terrifying danger of biological and immunological threats on Kepler-22b transforms the search for extraterrestrial life into a profound ethical challenge. It underscores the chilling truth that life, in its infinite forms, is not inherently benign or compatible. A world within the habitable zone, teeming with its own unique biology, is not an invitation for companionship, but a stark warning of an invisible, existential peril. The universe, in its boundless creativity, hides not only wonders but also biological nightmares, silently waiting in the dark, perfectly evolved to destroy anything that does not belong. End of hook section. The tantalizing promise of a world within the habitable zone often overshadows a crucial, terrifying truth. Habitability for whom? For humanity. A species perfectly adapted to Earth's gentle gravity, breathable air, and complex familiar biochemistry. Any truly alien world, even one seemingly ripe for life, could transform an act of exploration into an irreversible descent into terror. Kepler-22b, initially hailed as a potential second home, presents the ultimate test of this chilling hypothesis, painting a speculative horror scenario where humanity's ambition collides with an indifferent yet utterly deadly alien biosphere. Imagine for a moment an advanced human expedition, drawn by the distant siren song of Kepler-22b, perhaps centuries from now, with technologies far beyond our current grasp. Starships arrive in orbit, their crews filled with the same boundless optimism that once fueled the Kepler telescope. They see the shimmering blue sphere, the unbroken global ocean, and believe they have found paradise. Their advanced sensors confirm liquid water, a stable star, and a dense atmosphere, all textbook indicators of life's potential. They descend, perhaps in armoured submersibles designed for extreme pressures, or atmospheric entry vehicles built to withstand intense conditions, their mission to gather samples, explore, and perhaps, eventually, to colonize. The immediate reality of Kepler-22b would be a brutal, visceral shock. Upon breaching the planet's atmosphere, the sheer density of the air would become apparent. Instead of a clear, crisp descent, the craft would plough through a thick, viscous medium, buffeted by perpetual planet-spanning storms driven by the endless ocean's thermal inertia. The sky, a perpetually overcast expanse, would offer only a diffuse spectral glow, a muted twilight even at the brightest point of the day. Stepping out onto a floating platform or onto a rare exposed volcanic outcropping would be an exercise in extreme survival. The crushing gravity, perhaps 3 or 4 times Earth's, would render every movement agonizingly slow and ponderous. Human musculature, designed for a single G, would be inadequate. Bones would ache, joints would scream, and even lifting an arm would feel like raising a lead weight. Specialized exosuits, built for immense structural integrity, would be essential, yet they would offer only limited respite, transforming agile explorers into lumbering automatons. The atmosphere itself, dense and heavy, would press against every inch of their suit, a constant reminder of the planet's overwhelming power. Venturing into the ocean would be a descent into a truly alien hell. Even the most advanced submersibles designed to withstand Earth's deepest trenches would be pushed to their absolute limits, their hulls groaning under pressures orders of magnitude greater. The water, a suspected corrosive chemical soup, would relentlessly test the integrity of every seal, every material. Microscopic leaks would not be mere inconveniences, but catastrophic breaches, as the caustic liquid dissolves power conduits, compromises life support, or directly contacts human flesh. The constant threat of material degradation, the slow, silent eating away of their technological lifeline, would be a gnawing anxiety for any human expedition. Below the photic zone, the absolute darkness would swallow all light, a void so profound that even powerful artificial illumination would struggle to penetrate the swirling haze and chemical particulate, creating a claustrophobic, disorienting abyss. But the most insidious threat would be biological, an invisible war waged at the molecular level. The pervasive microbial life of Kepler-22b, perfectly adapted to its corrosive, high-pressure environment, would be an unquantifiable horror. These alien bacteria, viruses, or cellular organisms, with their exotic biochemistry and non-terrestrial genetic codes, would bypass every defense of the human immune system. A microscopic tear in a glove, a malfunctioning air filter, a contaminated sample, and the invasion would begin. Our bodies, utterly blind to the alien threat, would either allow the foreign agents to replicate unchecked, dismantling cellular machinery, or mount a devastating autoimmune response, destroying themselves in a futile attempt to combat an unknown enemy. The death would be swift and agonizing, a systemic collapse from within, utterly untreatable by any terrestrial medicine. And then there are the macro-scale horrors, the apex predators we speculated might exist in the abyssal plains. For human explorers, encased in their cumbersome suits and operating in near-total darkness, these hyper-adapted hunters would be invisible, silent, and deadly. Their advanced chemosensory and electroreceptive abilities would make human technology, with its faint electrical signatures and metabolic byproducts, glow like a beacon in their lightless domain. Humans, with their slow, gravity-impeded movements, would be pathetically easy prey, unaware of the impending strike until a colossal, powerful form materialized from the gloom, its specialized weaponry, crushing jaws, corrosive barbs, paralyzing toxins, perfectly honed for execution in its home environment. The psychological toll of knowing you are hunted by unseen superior predators in a realm you cannot comprehend, where escape is impossible, would be a horror beyond measure. Even the most basic needs, food and water, would become a source of existential peril. The alien biosphere, with its unique biochemistry, would render all local sustenance inedible, if not outright toxic. Attempts to process the local water could yield fatal compounds, and alien biomass would be metabolically incompatible, potentially mutagenic or instantly lethal. Any human expedition would be entirely reliant on dwindling precious supplies from Earth, turning every lost ration into a step closer to starvation. The very act of respiration could be compromised. Even if a breathable atmosphere could be synthesized, the constant pervasive biotoxins and reactive chemicals would relentlessly challenge life support systems, demanding filters and purifiers of impossible efficacy against an ever-evolving alien threat. In essence, Kepler-22b would not be a planet to colonize or even safely explore. It would be a planetary trap. The environment itself, from the crushing gravity to the corrosive water, the toxic air, and the omnipresent perfectly adapted life, forms an insurmountable barrier. The initial hope of finding a second Earth would curdle into a realization of profound isolation and lethal incompatibility. Any human outpost would not be a foothold, but a besieged bunker, its inhabitants slowly succumbing to unknown diseases, environmental degradation, or the silent, persistent predation of a world that simply does not care for their existence. Return to Earth, if even possible, would be unthinkable, for fear of carrying the planet's microscopic horrors back to our fragile home world. Kepler-22b would become the ultimate cosmic nightmare, a world that should not exist in our dreams of companionship, a chilling monument to humanity's profound vulnerability in a truly alien cosmos. End of hook section. Our journey through the theoretical depths of Kepler-22b began with an almost naive hope, a yearning for cosmic companionship reflected in the distant shimmer of an ocean world. We were drawn by the allure of the habitable zone, that celestial Goldilocks band where conditions are presumed to be just right for life, imagining a mirror of our own blue marble. This initial fascination, rooted in the human drive to find familiarity in the unknown, projected onto Kepler-22b an idyllic image of an Earth-like paradise, a beacon of biological promise floating in the endless void. It embodied our deepest aspirations for discovering a second home, a place where life might flourish in forms we could, perhaps, even recognize. Yet, as we peeled back the layers of this dazzling deception, the true, chilling nature of Kepler-22b began to emerge. The very parameters that rendered it so tantalizingly habitable also sculpted an environment of profound systemic hostility. The immense gravity, a silent, crushing tyrant, would not only flatten its geology, but fundamentally reshape any life, forcing evolution down paths of extreme resilience and terrifying adaptation. We imagined organisms built like living fortresses, their forms squat, dense and powerful, perfectly honed to resist a perpetual invisible adversary. This gravity, an inherent property of its super-Earth status, transformed every biological function into an Herculean effort, every movement a ponderous struggle against the planet's relentless embrace. It redefined the very concept of physical existence, making lightness and agility an impossibility, replacing them with a brutal efficiency born of compressive force. Below the surface, the dream of tranquil oceans dissolved into the nightmare of a perpetual twilight abyss. A global sea, perhaps tens or hundreds of kilometers deep, would be a realm of unimaginable pressure, where liquid water transforms into exotic ice phases and the very concept of an ocean floor is redefined. Filtered by a dense, perhaps toxic atmosphere, light would be a scarce commodity, plunging vast stretches of the planet into eternal darkness. And within this crushing, sunless realm, a corrosive chemistry would likely prevail, born from hydrothermal vents and interactions with the planet's deep interior, saturating the water with heavy metals, acids, or compounds that would dismantle terrestrial biochemistry with ruthless efficiency. This is not a nurturing bath, but a primordial chemical reactor, a vast, churning vat of solutions that could actively dissolve the very molecular fabric of Earth life. In such an environment, life would not merely survive, it would thrive in forms utterly alien to our understanding. Evolution, unburdened by our terrestrial biases, would sculpt apex predators of chilling efficiency, silent, powerful hunters navigating by electroreception and chemosensory arrays, their bodies perfectly adapted to slice through high-pressure liquid, their methods of attack brutal and decisive. These are not creatures of natural beauty, but living instruments of death, each a testament to the universe's capacity for creating terrifyingly perfect organisms, each a master of its own abyssal domain. Their existence would underscore a fundamental truth: life adapts to its environment, no matter how extreme, and in doing so, can become a profound threat to any unadapted intruder. But the most insidious horror lies not in the visible forms of life, but in the planetary metabolism itself. Kepler-22b, as a living, breathing entity, would possess a systemic biochemistry that could be fundamentally inimical to human existence. Its atmosphere might contain gases that are respiratory poisons, its waters saturated with biotoxins produced by alien plankton, its very geological processes perhaps releasing radioactive isotopes. The planet itself, in its indifferent functioning, could be a colossal biological weapon, its ubiquitous microbial life an invisible, relentless threat. Our immune systems, honed for Earth's pathogens, would be utterly unprepared for alien viruses or bacteria, which might possess chirality-reversed molecules or entirely novel genetic codes, rendering every terrestrial medicine useless. Even inert alien compounds could trigger fatal immunological cascades, turning the act of breathing or touching into a gamble with immediate agonizing death. This journey to Kepler-22b, from a glimmer of cosmic hope to a speculative scenario of planetary horror, forces us to confront a fundamental, sobering truth. The universe is not designed for us. The habitable zone is a scientific definition, a probabilistic calculation of where liquid water might exist, not a divine promise of human-friendly worlds. It is a spectrum of possibilities, many of which are profoundly, existentially terrifying. The cosmos is vast, indifferent, and infinitely creative, capable of sculpting biospheres so robust, so perfectly adapted to their extreme conditions, that they become impenetrable fortresses for any foreign biology. This perspective challenges the very hubris of humanity's outward gaze. We dream of finding life, perhaps even intelligent life, that mirrors our own, confirming our significance. But what if the vast majority of life in the universe is so utterly alien, so perfectly adapted to conditions we perceive as lethal, that any encounter would be a catastrophic biological mismatch? What if the Goldilocks Zone is often a cosmic trap, a beautiful illusion designed by sheer evolutionary pressure to produce systems that actively repel or destroy anything not of their own making? The universe does not owe us familiarity, nor does it guarantee safety. Our speculative horror scenario for Kepler-22b is not merely a tale of fear, it is a vital thought experiment. It underscores that understanding a planet's potential for life requires far more than just surface temperature and water. It demands a holistic appreciation of its gravity, its deep geology, its atmospheric and oceanic chemistry, and the vast unknown possibilities of alien biological evolution. It compels us to acknowledge that the universe is far stranger, far grander, and potentially far more dangerous than our anthropocentric imaginations often allow. In the end, Kepler-22b serves as a profound philosophical anchor. It reminds us that for all our technological prowess and scientific ambition, humanity remains profoundly fragile, a species perfectly tuned to the unique, improbable conditions of a single small world. The quest for other Earths, for cosmic companions, should not diminish but amplify our reverence for the one we already have. This fragile blue marble suspended in the cosmic dark is not just our home, it is an anomaly, a true miracle in a cosmos that is often breathtakingly beautiful, but just as often, utterly terrifying in its indifference. And sometimes, the greatest wonder of the universe is not the world we seek among the stars, but the one beneath our feet, the one we must cherish and protect, for it may truly be the only safe harbour in an infinite sea of alien nightmares.